So for anyone who doesn't know me, I'm Chris Taylor, and I'm not the main attraction. But as Associate Vice President for Digital Strategy and Innovation for the university, it's my great pleasure to introduce Sami's inaugural lecture. So, AI, which is Sami's area, is set to have a huge impact on the university. It's going to affect everything we do, from research and innovation, teaching and learning, social responsibility, and the way we operate as a large organisation. And to retain our position as a leading university, it's going to be essential that we apply deep expertise in AI across all of those areas, and that's something that Sami brings. So we were extremely lucky to attract Sami to Manchester to lead a significant investment in AI fundamentals. He's brought new energy and connections and has helped us recruit excellent colleagues to form the nucleus of a Centre for AI Fundamentals. Sami was first appointed to a chair in 2004, and he's led research centres since 2010. Alongside his position in Manchester, he's retained a position at Aalto University in Finland, where he also leads the Finnish National Centre for AI. Sami's research has been characterised by unconventional thinking, leading to significant breakthroughs. But he insisted, I should say, that the most interesting work is always facing the next challenge. So it's a real pleasure to invite Sami to present his inaugural lecture.
Many thanks, Chris, and I assume you are hearing me and not too loud. At least I can hear something from the mic. All right, so I'm very much a machine learning researcher at heart, but this is an unconventional machine learning talk. I checked this morning that I probably actually have 0 equations here, but everything underneath what I'm going to talk about is actually machine learning, and I'll be very glad to talk with anybody on the details of those. So what I tried to do now is to talk to 2 kinds of people, or spectrum between those. So anybody who wants to work with me or my colleagues on actually implementing the kinds of things or new principles for implementing the kinds of things that I'm going to talk about, or people who want to solve problems in other fields with techniques such as the ones that I'm going to talk about. So my students, or some of them, actually, the slide is not changing in this end. Now it is. Some of my students are saying that everything older than 6 months is so old that it's not worth reading or citing or taking into account, which often probably makes sense. But in that sense, I'm going to talk about 4 things that are ancient history. And the motivation for this is that I think many of us working in machine learning have noticed that many of the breakthroughs at the moment are actually revamps of some things that happened in the 90s, or sometimes even earlier with newest technologies. So these 4 that I'm going to show are going to be the next. I mean, if the fashion goes like 60s music, 70s music, they always come back. So now this is the next decade. So I'm hoping that this is the next revolution then when somebody finds time to do these again. So I'm showing a few examples. So this one was when we started working with Nokia, which actually had the first see-through augmented reality displays with eye tracking installed. So we started asking what would be the coolest thing you could do with this. And well, there might be something even cooler, but what we thought about was information access where you don't have to search. So it would be automatically contextualized based on what you happen to be looking at. And of course, realizing that it's not just what you look at, that would be a Midas touch. So you don't want to see absolutely all background of everything you happen to see or watch at. And it turns out that our eye tracking data is actually very noisy, and it is of course a reflection of everything we are purposefully doing. So it's not quite that simple. But that, on the other hand, is then an interesting machine learning challenge. So the principle was, conceptually, it's very simple. So we would just have these display devices, then we would observe the interaction, which in this case is the case tracking data. Then we would infer what was relevant for the user, what the user might want to find more info about. Then we do context-sensitive information retrieval, place it on the display, and then now that we have augmented the reality with whatever was pulled out in the information retrieval, now we can also observe, did the user actually pay attention to those, and now we can create a loop based on which the user's interests can be also inferred. And this actually worked really well. I don't know why they didn't push it forward, but I bet that Apple now will. So the key idea there relating to machine learning was to do infer based on the observations of the user what they might be interested in, kind of implicit feedback. We then later did the same with brain signals. That didn't work so well, but it worked better than significantly better than other approaches. But yeah, that's not a breakthrough. This is an example which actually works. Is here we are not augmenting anything, and we are not observing the behavior. The behavior is actually purposeful. So the user chooses what they want to see in information retrieval, but what we are changing is how are we showing things to the user, and we are trying to adapt that so that it's easier to choose the things that the user is likely to want to choose. So it's kind of the automatic text prediction, or also, of course, that's how much of the natural language processing now works. You can do the same also for finding data sets that you need in data science, and maybe the low-hanging fruit that we could do, we actually did model search as well. For the potential future, everybody thought I was crazy, that people would be storing models and then somebody else might want to reuse them, or at least want to use somebody's priors. I mean, that's madness. Who would believe on my priors? But now, of course, the pre-learning of the deep networks, I mean, you would want to do exactly this kind of a search, right? You would want to find out exactly the right pre-learned models to build on in whatever you want to do. Again, you can do the same thing that I said. Let's transform the display to match to what the user wants to do, so that those things that the user wants to do, or more generally, the decisions that the user wants to make, or utilities the user wants to maximize, are easy to maximize given the arrangement of the display. And here's an instance which I think is probably the lowest hanging fruit. This actually could be done by the NeurIPS deadline this year, which is still in May. So I'm just giving some hints here. So the bottleneck in this was that the computation was too heavy. I think this algorithm works really nicely, but the computation was too heavy. And nowadays, of course, we would know how to amortize this with neural networks, pre-compute and amortize. One more of the ancient history. So this is about multi-data source machine learning. In this case, applied to drug sensitivity prediction. So the task is to predict missing entries in the matrix, which is patients versus drugs. And the entry is telling whether this drug is likely to work in the personalized medicine sense for this patient. So if we can fill in the missing entries here, and if we can extend this matrix to new drugs and new patients, then we can run personalized medicine on this. And this one actually won some prizes as well. I think this is not anymore the bleeding edge, of course, because you would need to replace the arrows here by deep learning, which we didn't do. We had linear models at this stage. Anyway, that's the prehistory. And when I was looking through my old slides to find these, I realized that I actually might want to do the same with the deep learning, but I don't have the time, so if anybody wants to grab these, so go ahead. What I wanted to talk about next is what I have been thinking for a long time is that what's the best I could do for the humanity. I'm sorry about these grandiose terms, but I mean, many of us are thinking of what could we do instead of working for the big tech and solving the boring problems. So what is the best I could think of doing as a computer scientist? Because I don't think I could be the best biologist or I could be the best physicist or something like that. I should have started much earlier. Now it's too late. But what I might be able to do is to improve the general problem-solving method that we as humanity have, even by epsilon. And if I can do that, then of course across all the problems that can be solved with that general problem-solving methodology would average, integrate out to be a really large contribution. And what that general problem-solving methodology is of course scientific research. So is there something we as machine learners or I as a machine learning professor could do to achieve this, or even a small epsilon improvement? So the current main mode of collaboration between AI researchers, machine learning researchers and other fields and companies is that most work with one collaborator or maximally a few collaborators. Of course, there could be, and sometimes is, a network of these collaboration links, because different expertises, multiple different expertises are needed for solving a practical problem, and that's what these links would show. So what could be done better? So now some companies have realized how this is done, and they release datasets, or they release a so-called GIM, so a benchmark problem for the machine learners to work on, and then machine learners would actually work for free for this. I think this started with the Netflix prize, and there have been several others since. Some fields of research have also done this, releasing datasets and machine learning problems. And of course, those who do this are winners because they get machine learners to work for them for free, or at least very cheaply compared to buying the same expertise from the market. So how can we make this easier? I mean, this would be good for science, especially if new resources are pouring in, as this is done, and it's not just zero-sum game between the companies. So how can this be made easier? So what is underneath research is starting from the earliest days of empirical science. There is underneath the research, there is a cycle that is called in different fields design, build, test, learn cycle, or design, make, test, and so on. Here's an instance from drug design. So what has changed recently is that in all fields, there is another loop that is run based on simulations, which are much cheaper, much faster than always going through the real world. I think we are all seeing still the slides, even though something happened on this screen. So tell me if not, I mean also remotely. So now the question is, can we make this somehow faster, more efficient, given that most of the work is happening in simulations and then only more seldom going to the real world? So the state of the art, how this is done at the moment, is that each field seems to have their different toolboxes for running essentially the same operation. So if I take an example, Bayesian optimization, which is a straightforward tool for doing something like running this loop, each of these fields that I'm mentioning here, 3 examples, actually has their own toolboxes, which brings up a rather obvious idea, so that there's a scale advantage here. So doing it only once, but a better tool, or then the others reusing what the others developed, which gives now the keys on what we could do much, with easy effort, we could do much more to make science more effective and efficient. This also brings a new opportunity, which is that if everything is now done based on simulations, we could now ask that could we build more intelligent tools which would be able to help people do whatever they are doing in those simulations, the experimental designs, more effectively. And that's what I would call collaborative AI for science. And what is needed for this is we can see the simulations, the environment in doing the simulations as a virtual laboratory, and here I don't now mean augmented reality, I simply mean simulation-based, virtual as in simulations versus the real world. What we would need for that is essentially digital twins. You can use your other favorite terminology, like call them just as models for here. So of the thing that we are studying, of the instruments that we are studying the process with, and why the instruments, because the people who are experts in that field are accustomed of interpreting results in a certain way. So having a digital twin of the instrument, like a microscope, will make it more interpretable to them. And if we want to have collaborative AI assistants, then essentially I will be arguing in the following, we will also need to have some kind of a digital twin of the researcher. And now I don't mean having a fully blown digital twin of humans, obviously not. Likewise, as we don't have a full-blown digital twin of the ecology if we are doing biology, just the relevant things. About this collaboration, what can we do there? So if the traditional way of doing things is that we have a user, a researcher, who is doing something with the real world, making interventions, observing some things. Now, most of my colleagues, machine learning colleagues, are actually thinking of this loop and thinking of automating this. And that's kind of the mindset. So can we do the same operations, essentially finding out more about the world or modeling the world more automatically? Which of course makes sense in many applications, but not in all. Often there is an expert who has knowledge and in particular is the only one who knows why we are doing this and wants to steer the whole process. So what is needed to help that expert? We are not taking the expert out of a loop. How does our machine learning problem then transform? For some reason I can't get now the figure here. Oh, here it is. All right. So what is needed is that instead of building a model of the world, so let's say a material, if we are doing materials physics, we would want to have a digital twin of the material so that we can design it better, a better material. So we need instead to have a joint model of the researcher optimizing the material, and the AI wouldn't know, which is then trying to help the researcher, wouldn't know what is the goal of the researcher and needs to find out as a part of this process. And the AI would make some recommendations to the user on what to do next. I noticed that surprisingly few people are thinking of these kinds of things. So my machine learning colleagues are always, I get a blank stare on humans, come on. Obviously we want to automate, and this is very difficult, by the way, and yeah, we would need to learn about humans. On the other hand, user interaction researchers or psychologists that I work with wouldn't be thinking of AI in this sense at all. It would be human-centric in the sense that let's put in an artifact and see how humans interact with it, instead of thinking as an engineer, how do we design the AI so that it would be maximally good for that. That's why we wrote a hopefully easily digestible piece to the AI magazine, so that it would explain what we are doing for both of these communities. So now taking the example of drug design, we would have a designer who has a specific drug molecule in mind and is thinking, planning, how should I change this to have more of the properties I want to have and less of the properties like toxicity that I certainly don't want to have. Now the AI can help by automating this. If it needs to make a recommendation on what to change, it will be completely out of place if it doesn't take into account what the researcher is thinking at the moment, what kind of changes. Right? That's why it needs the user model. If we start formalizing this, we would have an agent, which is now the user, which is acting in an environment, observing the state of the environment. This is like the reinforcement learning setup, but now the agent is the human. And what we are doing, we are installing the assistant whose actions are recommendations to the user, but the user is completely in control and decides whether they accept and implement those changes in the world. Of course, other formulations are possible. What we tried to do with this formulation is to say what it means if the user is in the loop and in full control. Of course, the agent could also, assistant could also act in the real world as well. That's then a different formalization. Two instances of this kind of setup. One would be personalized medicine. Now the agent is a doctor who needs to decide a treatment for a patient who is the environment, and now the AI assistant would be recommending a subset of the available treatments and give its predictions on why the assistant thinks that these are worth considering. Design, like the drug design that I already explained, so the design change would be what the designer is doing, and the recommendation would be a set of possible changes worth considering, given what the agent is likely doing at the moment. In both cases, the utility, so the usefulness is only available after some time. So this is delayed reward decision making. An instance with a simple interaction would be in drug design, where we now begin to have generative models that are able to spit out candidate molecules if we are able to specify what properties they should have, if we have a score function. Turns out that we humans are pretty bad at formulating those score functions, even experts, so that they would capture exactly what they want. But what is much easier is to give just binary feedback for some of these candidate molecules that the system spits out. This seems promising for what I want to do. That doesn't seem promising at all. And then we can, with machine learning techniques, of course, try to reverse engineer what was the reason why they gave this feedback, and dress that up as the score functions or other steering signals, and then produce next better set of molecules. Wrapping up this virtual laboratory stuff, so what we need for doing this so that we can have maximal impact across the different problems, across the different fields, we would need software. I don't believe in monolithic software, but essentially we need open interfaces so that each field can implement their own models and make their operations accessible to machine learning tools that machine learners would develop for any field, so that the same tool can be used across the fields. So it seems simple. Why don't we have these virtual laboratories widely yet? And in particular, why don't we have these AI assistants? Because now what has changed radically since when I started doing this line of work is that now we begin to have large language model-based assistants. So it's very easy to cook up a quick and dirty assistant that can be amazingly good. And for that, I don't have a full-blown solution yet on RV or a full-blown mature opinion on whether we should all move to doing that or developing those techniques or some combination, or should we be thinking of the theories at all. But I'm highlighting a couple of problems that we need to solve, irrespective of which of these roads we take. So the first one is that humans are not, for good and bad, are not just data sources. So what I showed earlier, they were instances. In those instances, the assumption always was that the user is giving information. I mean, if you see a paper that has human in the loop machine learning in its title, it typically would mean that instead of measuring in the real world, the system is asking for information from the user, with the assumption that the users are at least trying to answer very truthfully. So now what I'm arguing now is that even in these simplest cases, we actually usually don't, which was at least a bit surprising to me that it's so salient. So now we designed a simple game, so Bayesian optimization game, maximize a function that the user is playing with an AI. So the AI is trying to find the optimum of this function, maximum of this function, it doesn't see the function. It only sees the points that the user gives when the AI asks. The user does see the function. So now on the right, here you can see the circles are 2 points that the AI has asked, and now it is asking the user for the function value at xq. If I'm doing this, I would be thinking that the AI probably has some representation in mind. I wouldn't be thinking in terms of mathematics, but I would be assuming that it thinks that the function probably goes close to the observed points where there are observed points. Elsewhere, it has no clue. So if it is at all clever, it has some uncertainty estimate. So it would look something like this. So the dotted line is the mean, and then it has some uncertainty estimate around it. So now when it is asking me what is the function value at xq, if I would give the answer, if I would just answer the function value, now what it would infer, because it probably assuming that the function is smooth, it would infer that it's very unlikely that the true maximum is so close to this point as it actually is. So it would take a long time for the AI to ask questions until it realizes that, oh, initially it thought wrong. I need to correct my views, right? But nobody told that I must tell the truth, right? If my goal is to just get the AI to solve this question quickly, so what I can do is I can answer like this. So and my interpretation to this would be that, yeah, it's almost there, right? But I can only answer with the function value, so I'll twist the reality a bit there so that the AI gets the right answer quicker. And of course, this was just me explaining how I might think of this. We of course needed to run a user study to check, do others also think in this way? And it turns out that they do. So if users are playing this with an AI, instead of the AI getting the correct function value as answers, which is the Bayesian optimization here, the users are able to help the AI much quicker find the optimum. And it turns out the curve on the right shows that the more the users twist the kind of immediate reality in order to help the AI, the more they can help the AI. And the users were not instructed to do this, right? This really comes naturally from us. Now we can think of what does that mean. So I think it means that we have some kind of a simple theory of mind even for AI. And these were, by the way, these were not Bayesian optimization specialists who might have thought of this as Bayesian optimization. So this raises the question that when I started saying that for assistance we need to have a joint model of the user and the world. So what does this imply for what kinds of user models do we need to have? So my interpretation is that the users are goal-oriented. So what does that imply for us as machine learners? So goal-orientedness or being active with a goal in mind, that's sequential decision-making. In economics, there is, and that would be formulated as Markov decision processes or partially observable Markov decision processes. In economics, there has been a really long discussion, I don't know if it has converged yet, on are humans rational? And now we can start arguing about this, but the important thing to notice is that what they mean by rational is with unlimited resources. So it doesn't take a nanosecond for me to answer that, no, we are not rational in that definition. But what I would tend to agree, that we are rational with limitations, right? So of course, I have a limited time to answer a stupid question that the AI asks me, and I might not put a lot of my resources to that. But given the resource that I put there, it's more likely that I would do something that's useful for me than that I would do something that's useless to me. So simply, how I would put this is that it's unlikely that anybody would willingly shoot themselves in the foot unless they think it's good for them. Okay, so this is already, this principle now begins to be enough for us to start building user models. It may not seem so, but I think this gives us a handle on how we would start formulating these. And then what is needed computationally, because underneath there is somewhere there is a reinforcement learning problem, which is the forward solution to the problem, reinforcement learning with limitations, and then inverse reinforcement learning if we want to infer what are the goals of the user. We might be solving those problems with not the standard old-school reinforcement learning algorithms, but instead with generative models, for instance. But the problem, of course, underlying problem is still the same. I'll highlight another thing that we absolutely need from the user models, I think, and I hinted at that by saying, using the word theory of mind. So the simplest assumption in human-in-the-loop machine learning is that the users will just give information without thinking about it, right? And that would be the level 0 user model here. Level 1 would be, these are the assumptions that the AI is making of a user in the types of collaborative AI questions that I have been talking about. Level 1 would mean that the AI realizes that the user actually has a goal. So this is necessary for solving the Bayesian optimization game. The next level would be that the AI realizes that the user has a goal and also realizes that the AI has a goal. Now we can of course build a homunculus out of this, which will make this unsolvable if we don't know the level at which we are operating. My argument would be that probably level 2 is plenty for doing most of the things we need to get done. So revisiting the question, why don't we have these yet? So now I've given the keys of solving everything, and these keys have actually existed for at least 5 years or so. The problem is computation. So now if we put in the nested model that I now described and try to do inference online with that based on every single new observation that we get from the user, if we do a brute force solution even with a very simple user model, that would take hours to compute, update the model, even the simplest possible model for one new data point. But now we can do what is very fashionable at the moment, and we can amortize, what is called amortization in deep learning literature at the moment, which means that we would pre-compute solutions, use them as data, and then compute a surrogate, deep learning surrogate, which is able to predict almost in real time what the answer should be. And now we can kick with that machinery for the user models that I have been talking about. On the left, there's a simple example on a maze. There's an agent working in a maze, and the assistant is trying to infer what is the goal of the agent. If you amortize with the so-called neural process, you can get to performance that is very close to an oracle, which knows the correct answer, in contrast to using meta-learning, standard deep learning solutions applied in a vanilla way, and so on. On the right is a very simple real user model case, about the simplest user model that I can think of, which is a menu search. So now the model is trying to model what the user does after seeing a menu, and now the assistant is trying to design the menu so that that kind of a user will be able to find what they are looking for as quickly as possible. And it turns out that the computation becomes completely feasible in real time. Now we are talking about milliseconds, and the results are actually able to help the user, reduces the user's time in here. I thought to wrap up by showing, looking into the future a bit and showing 3 challenges, and then telling something about collaboration opportunities quickly. So the state of the art in many things at the moment is what is called generative model or foundation model, computed once from a massive data set and then applied in problems afterwards. And of course the large language models that we all are familiar with would be an instance of this. So now if we don't believe the pep talks that we will at some point in the very near future have one massive foundation model that will be able to solve all our problems better than any other models, the so-called artificial general intelligence, then we probably will instead have what we seem to have already now, is that we have field-specific foundation models. And now the problem I'm highlighting here is that even if I'm wrong in picking the exactly right estimate here, but computing one foundation model will produce about 100 tons of carbon dioxide in the atmosphere. And now if we don't believe that one model will solve them all, then we will need to have plenty of models. And in particular, solving any hard problem requires expertise from K domains, if we say K domains. And each of them is in one foundation model. Now the humanity will need, if we have n of those, and we typically need k, so then we'll need this many foundation models to be computed, because there is no technology at the moment on combining existing foundation models. You have to recompute a new one. This may of course change, and kind of knowing that it's the 6-month rule, but it may be that I'm completely wrong with this already because I didn't do a new literature survey. But anyway, that wasn't possible 6 months ago. Now there are certain solutions, for instance, one that we published in New York this year, or sorry, last year, came out this year. The other problem, which is even more grave, I wonder how many have tried out machine learning and realized that it doesn't work. People are really shy. I don't have any hesitation. So of course, kind of any machine learning that I have programmed will certainly not work, at least in the first go. But that's not what I mean here. I mean the basic assumption. So the basic assumption is that we have a learning data set, we learn a model from that, then we apply it in some other set, right? Now if we are thinking of seriously about real world, the assumption underlying what I now said is that the learning data set is representative of the test data set. And of course it never is. I mean, statistically saying that they come from the same distribution or close enough. It never does. There's always some factor that comes at play, right? Something that we didn't anticipate, which is different between the learning and test data set, which is very well known in medical applications in particular. So what we need to do is to take into account the different conditions, be either robust with them or then be quick to solve the problems. Third challenge, this I actually already hinted at. So if we have good solutions in n fields, is it really so that we can solve the n plus first field any better? And the virtual laboratories would be the solution to this. All right. Lastly, just telling very quickly about the collaboration opportunities. We are today launching the AI Fundamentals Research Center, and because we are very serious about AI fundamentals, we call it AI Fun. So as Chris mentioned, there are now really good new academics that the university has invested in, and new ones are coming. I think Omar in the front row has not started yet, but is already here, and there is a couple of others. So these are people who are focusing mainly on AI fundamentals, machine learning, but that doesn't mean that they work in an ivory tower, simply because it's better to do machine learning research, even if that's their primary interest, in collaboration with other fields, which give inspiration for the problems. Additionally, we might actually label the whole university AI Fundamentals Research Center, because absolutely everybody needs these, as Chris was saying in the beginning. But it might make more sense to call those people who want to work at the AI Fund Center, but whose main focus is elsewhere, but who are still serious about AI fundamentals, call them, for instance, associate members or something like that. And we, of course, have really good people doing that. And lastly, I wanted to say something about the specific things that I am bringing to Manchester for free. And now I'm going to reciprocate on showing these kinds of slides when I give presentations in Helsinki, now that we have these materials. But two slides summary of what is the Finnish Center for Artificial Intelligence. So it's a flagship of research of the UKRI of Finland, Research Council of Finland. It was a competitive call across all the fields. We won that with AI Center. It's trying to do world-class fundamental AI research and transforming other fields with that. Sounds very much like what we are wanting to do in Manchester in tightly knit European collaboration. And one element of that, of course, is the Manchester-Helsinki collaboration then. I think it's fair to say that this has been a success story based on the numbers or the results, but not go into details on that. I'll just finish with some timely adverts where the thing that might seem obvious, but which is by far from being obvious, is that I have a web page. That has been a long time coming. I haven't had an up-to-date web page for 10 years, so there it is. We as others are recruiting all the time. I want to particularly emphasize another thing. There's a launch event also of the Manchester unit of the European Laboratory for Learning and Intelligent Systems, ELLIS, which is running, for instance, in Manchester, a really attractive summer school. I'm also running another summer school on collaborative AI and modeling humans in Helsinki. And we are running the ELLIS robust machine learning program for ELLIS, which has 2 workshops this summer, Helsinki and Oxford. If anybody is interested in what I talked about in this, how do we anticipate changes that may happen between learning and testing. And that's it. Thank you for your attention.